everybody. I'm Mark Tewksbury, your host for this program. Our goal is to reveal the materials and methods that turn out the everyday products we see around us. If you think you know something about these items, you might be in for some surprises. There's a whole world waiting for us to discover here on How It's Made. We all know butter comes from cow's milk, but did you also know that it can come from a camel? In olden times, when Arabs rode their camels, they hooked a goat skin filled with camel's milk to their saddles. The camel's ungainly walk stirred the milk, thereby liberating fat globules and forming butter. What a great idea. On today's show, steel, apple juice, aircraft landing gear, and cosmetics. Remember Superman? He could leap over a building with a single bound. He could also bend this with his bare hands. Bridges, skyscrapers, appliances, our lives revolve around this material called steel. Steelmaking usually begins with a pile of scrap metal. Using this 10-ton electromagnet, scrap iron composed of crushed car bodies, electric appliances, cans, and other steel scraps are gathered up. This powerful magnet is able to lift 5 tons of metal. About 83% of this scrap will be transformed into bars of steel. This metal is then dumped into a basket, which by itself weighs 32 tons. The basket can hold up to 60 tons of metal, and now they're going to melt the metal. This furnace reaches a temperature of 1650 degrees centigrade, hot enough to liquefy the metal. It is heated by 3 electrodes and by 4 natural gas burners. The contents of the basket are dumped into the furnace. Here, the pieces of metal come into contact with liquefied steel, which always remains at the bottom of the furnace. There's a reaction, and an aeration system draws out the smoke that's produced. At this high heat, the 60 tons of metal will melt in about 60 minutes. Then the cover is placed on the furnace. This liquid is composed of impurities, which rise to the surface when the metal becomes molten. At this stage, a workman draws a sample of steel to determine its chemical makeup. And now they make use of a supersonic oxygen lance. This lance blows oxygen into the molten steel, which reduces its carbon content, homogenizes the mix, and then speeds up the melting process. A ladle is positioned beneath the furnace. The molten steel will be transferred from the furnace into this ladle. The molten steel easily pours into the ladle. The ladle weighs 55 tons and holds 115 tons of molten steel. An overhead crane capable of lifting 180 tons carries the ladle filled with steel. Additives are introduced in order to obtain the correct steel tone. Here, the electrodes are taken out of the furnace ladle. A workman now opens the pouring nozzles of the distributor, equipped with 4 pouring holes. The molten steel runs into molds. It very quickly cools and begins to harden. Steel billets are produced in lengths varying between 4.5 meters and 10.6 meters. The billets are then cut to the desired length with a natural gas torch. A pouring identification number is marked on them with a wax crayon. The difference between a steel billet and the nearly finished flattened product is clear. Flattening of the billets remains to be done. Before flattening begins, billets are placed in the furnace to be reheated for 2 hours at 1095 degrees centigrade. Water jets cool the billet ejector. The billets are placed on the flattener, where powerful rollers compress them. This operation gives the billets the required shape and size. Water-cooled rollers crush the billets. Some billets go from a thickness of 12 centimeters down to 14 millimeters, while others reduce from 15 centimeters down to 19 millimeters. At the end of production, bars move along at a speed reaching 35 kilometers per hour. Once reaching their required dimensions, the bars must be cooled. This cooling bed allows the steel bars to cool uniformly. A total of some 400,000 tons of steel bars are made at this plant each year. Put thousands of these into a big press, apply literally tons of pressure, and what do you get? Apple juice, of course. Some people like me drink gallons of it every single year. Here at Rougemont, they make apple juice mainly from Macintosh apples. Some 90% of juice production is done at the harvest time in October. A conveyor transports apples to an inspection location. Apples tumble in the reverse direction of the conveyor belt so that wet leaves and undesirable materials adhere to the belt. The apples are stored in silos for several hours. In order that the apples are not too bruised in their descent, they're slowed down in this stepped chute. Juice making can now begin. Now they wash the apples. This first water bath eliminates pebbles since they also use apples that have already fallen from trees. A shower of cool water completes the washing process. The apples are then cut into little pieces in this grinder and produce gratings. Enzymes are added which break down the cellular structure of the fruit, allowing for maximum juice extraction. Next, the gratings are transferred into maceration reservoirs where they'll stay for 60 to 90 minutes. Then they extract the juice. The gratings are pumped into a powerful hydraulic press. Inside the press, filter sleeves hold back the skins, seeds, and stems of the apples. Quality control is strict. At each stage of the process, they draw off samples of juice to evaluate its quality and to make sure that fabrication parameters are well adhered to. The juice is filtered a first time. The very smallest undesirable particles are held back by this sieve. The fabrication process continues. Juice flows from one stage to another via these immense reservoirs. The next step will be pasteurization. Juice enters this exchanger at 22 degrees and is heated up to 88 degrees centigrade, then cooled back down to 50 degrees. Enzymes are then added to hydrate the pectin and facilitate the second filtration. This is the ultrafiltration process, where filter membranes with microscopic pores retain the smallest of particles. The apple juice is now perfectly filtered. Its clarity is verified, as well as its flavor, color, and natural fruit sugar content. Since juice is produced in October, it has to be conserved throughout the year. A portion of the production is stored in this sterile warehouse area to await being bottled during the year. Each reservoir can hold 110,000 liters of filtered juice. No preserving agent is added. Now we move to the next stage, which is the filling of the containers. These little drinking containers are filled at the rate of 100 a minute. The containers are then hermetically sealed. Two little sprays of hot glue are applied to the containers. This secures the straws attached onto their sides. Another automated production line fills bottles with juice. They circulate in a row on this conveyor. Bottles are washed and disinfected with hydrogen peroxide in this white sterile room. Then they're rinsed with sterile water before being carried to the filling location. Each minute, 120 bottles are filled with pasteurized apple juice and sealed with a cap in a sterile environment. Bottles are then labeled and sent to shipping. Between 20 and 40,000 tons of apples are transformed into juice yearly. Thanks to its perfect preservation, consumers can enjoy this juice at any time of the year. Flying is great, but easing hundreds of tons of aircraft onto a runway safely requires some pretty sophisticated landing gear. Let's see how it's made. This heavy piece of steel is the undercarriage of a KC-135R airplane. A landing gear comprises a central shaft to which an axle and wheels are attached. They begin machining the shaft. This digital lathe machines the exterior surface of the part. Sprays of water and oil cool the part, which heats up due to friction. They're now going to pierce the shaft. This drill head will remount the inside of the shaft. Alignment of the head must be perfect, so they're cautious with their work. The perforating gets underway. Turnings from the cutting are saved, and these will be sold to foundries where they'll be recycled. We see here the cutting tool used to pierce the holes in the landing gear. To perforate the part, very sharp cutting tools are used. Here, they complete an attachment hole. The hole is enlarged on its sides as required by this machine tool. The part is cooled with a mix of water and oil. Cutting is completed and the hole is now cleaned out with compressed air so that they can proceed with a visual inspection. Here, 3 pieces are rough cut at the same time by this machine. Because they'll be used in aviation, these pieces have to be machined to perfection. The machining of the shaft is now almost completed. This deburring unit polishes the machined surfaces with a compressed air tool and sandpaper discs. And now they have to verify the dimensions of the parts. This digitally controlled machine has 3 axes and does the verification with extreme precision. Here, another unit allows for the machining of parts with greater dimensions. This facility also reconditions used landing gear such as this one from a Boeing 707. They strip off the paint with a sandblaster to verify the condition of the parts with great precision. And here are those parts stripped clean. But a visual inspection is not enough. They can detect cracks by magnetic particle concentration. They magnetize the part and any cracks will become visible under ultraviolet light. Now it's time for the shot metal procedure, where they spray steel balls onto the metal surface to increase its resistance to fatigue. Before repainting the part, they first plate it. The part is immersed for 10 minutes in cadmium, which forms a protective coating on it that will resist corrosion. Then the part is quickly soaked in a weak concentration of chromic acid. Water, agitated by air jets, cleans away the chromic acid, and the part is rinsed with water another time. The part is now baked at 190 degrees over 23 hours to remove hydrogen induced during the plating process. Then the part is immersed in liquid nitrogen at -129 degrees centigrade before it's inserted in order to reduce its size. This collar is easily pushed on with a hydraulic jack. Reheating the collar makes it return to its normal size. Now the different components and the leak-proof joints are inserted into the piston. The shock absorber tube goes into the piston. This part absorbs the shock stresses when an aircraft lands. The piston is now slid into the cylinder, and they verify that the shock absorber is leak-proof. Fabrication finishes with paint baked in an oven. Some 6 to 8 months are required to make a new landing gear, and between 6 to 8 weeks to recondition a used one. When the old-time vaudeville comic shouted "makeup," he was unceremoniously smacked in the face with a giant powder puff. Today, we take makeup much more seriously. During archaeological excavations, mummies were discovered wearing makeup, the Egyptian technique of enhancing eye contours with antimony, lead, and metal oxides, all toxic, lethal substances. Greek women also adorned their cheeks with a dye made from lead oxide. In 1910, Florence Nightingale, under the name Elizabeth Arden, would change the whole makeup picture, launching the vogue for cosmetics without toxic agents. Cosmetics have been in existence since the dawn of time. There are many ingredients that make up a cosmetic formula. The industry heavily uses iron oxides to color its products in a multitude of attractive tones. Before moving into fabrication, each ingredient must be carefully and accurately weighed. These raw materials are often dry, such as powder, but can also be liquid, even oil or wax. Every ingredient will have first been approved by the Quality Control Laboratory. A single formula may contain over 50 ingredients. The other essential ingredient is water. The water used in making cosmetics is first purified by an inverse osmosis system. When it meets strict company standards, it is put into a stainless steel tank. Depending on the complexity of the recipe, between 4 and 10 hours of work are needed to make up a product. Let's begin with a bubble bath recipe. A part of the recipe is prepared in an adjoining container to make certain ingredients more soluble. A stainless steel screw propeller mixes all the ingredients thoroughly. All along its fabrication processing, the product will be subjected to many tests. Here, an acid-based neutralization reaction test is performed with a color indicator. The bubble bath has to be colored. A fragrance and a color are added. For in this recipe, the final product will be mauve. Before the filling process, the quality control and microbiology laboratories make sure that the product meets strict quality standards. Now it's on to the next step. This filler can simultaneously fill up to 12 700 milliliter bottles at a steady pace of 50 per minute. The fill level is adjusted electronically. Capping remains to be done. This capper positions and tightens the caps automatically. Urethane rollers apply the precise tightening force. The bottles now pass beneath a sealer via induction, which generates a magnetic field, heating the metal piece placed in the cap. When hot enough, it welds itself onto the neck of the bottle. Another product made here is the peeling mask. The mask is poured into this funnel, whose end is attached to the tube filler pipe. The product descends via gravity. The filler pours the peeling mask into 50 tubes each minute. Then, with heat and crimping, the tube end is sealed, and the tube heads for packaging. Other products made here, cologne and eau de parfum. The liquid is drawn into the bottle by suction. This rotating filler operates with intermittent vacuum to fill 50 bottles a minute. Bottles are positioned beneath the 16 filling spouts, which seal their opening to allow for the creation of a vacuum which draws in the product. Now atomizer pumps are inserted, handling 2 bottles simultaneously This machine seals the pump, securing it around the neck of the bottle. We see the white sleeve aligning the pump, while the gray one tightens the pump. Then there are the sprayers. This machine applies the spray stoppers and, with a hammer, presses them onto the pumps of the bottles, which are now finished. And one final product, roll-on deodorants. This machine fills 115 bottles a minute, handling 8 bottles at a time. A filling stem pours the product into the bottle, and here they place the roller ball at 115 per minute. Then the ball is lightly pressed into the cavity in which it turns freely. This plant makes over 1,200 different products and yearly sells 32 million items. If a picture's worth 1,000 words, I hope what you saw today speaks for itself. We wanted to take you behind the scenes to the world of manufacturing. I'm Mark Tewksbury. See you next time on How It's Made.